Okay. Okay, thank you. I'm Guoxin Zheng, coming from the University of Michigan, and today my topic is spin zero effect and large Landau G factor in cesium vanadium antimony 135 compound. This is the outline of the topic. First, I'm going to introduce some background on the cesium compound, like the superconductivity and the charge density wave, and also the rich features in quantum oscillations. Next part is our experiment. We did the PDO measurement in pulse magnetic field, and then we got some results like the spin zero effect and large Landau G factor. And the last one is our summary. First, this cesium compound is a Z2 topological Kagumi metal with a superconducting ground state. Figure A here shows the cooling down process. If we look at the here at around 94 Kelvin, we will see the first transition. This is a CDW charge density wave transition. And if we keep cooling, we will see the next transition at around 2.5 Kelvin. This is a superconducting transition. And figure B here shows the crystal structure, which is a layered Kagumi metal. And the UCSB group, the Stephen Wilson group did a great job in the this measurement of this material. They first did the SDH effect measurement, the quantum oscillations in the magnetoresistance. Figure A here shows the resistivity under the magnetic field. And here we can clearly see the quantum oscillations. And figure B here is the FFT analysis of resistivity. Here we can also notice there are several peaks, which means this compound has a complicated Fermi surface, as shown in figure C here. Figure C is a calculated Fermi surface, which is a nearly cylinder shape, which means this Fermi surface is two-dimensional. So and later we will mainly focus on the B1 orbital here, which is also has a two cylinder shape, 2D orbit. And this is useful information. We will talk about this later. And next is our experiment. What they did is put the material in the low field, and we want to put the material in the high field to see what will happen. So we did the experiment in the pulse magnetic field using the proximity detector oscillator, which is a contactless SDH effect study method. And figure A here is our setup. We have the coil and the sample. Figure B is the picture of our coil, and figure C is our when we put the sample on the coil. And basically, we have for the PDO we have the megahertz source, and we detect the frequency, the resonance frequency of this source. This source will pick up the change of inductance. So we can detect the change of frequency. This is related to the change of inductance, and the inductance is also related to the resistivity. So finally, we have the equation here, the last one. The change of frequency is proportional to the negative change of square root of resistivity. So which means if we can measure the change of frequency, then we can measure the change of resistivity. So we can track the SDH effect. So we did this. This is our experimental result. This is the PDO frequency versus the magnetic field. You can see we measured up to 72 Tesla, which is very high magnetic field. And here the definition for the angle is between the C-axis and the H magnetic field. You can clearly see the quantum oscillation here. And here our frequency will decrease when the magnetic field increase. That's because we said before the change of frequency is proportional to negative change of resistivity. So the negative trend here confirms the positive MR data. So they are consistent with each other. And so if we subtract the background, we can get this beautiful quantum oscillations again. And if we look at this dash line here, this means a fast quantum oscillation at around 800 Tesla frequency. So if we look at the amplitude at around 90 degree, the amplitude, the fast oscillation amplitude will nearly vanish, and also vanish again at around 37 degree. This is unusual because we know the amplitude for the FFT for the quantum oscillation will vanish, will decrease monotonically. But here it decrease and show up again, and then decrease and show up. So this is unusual. So we want to analyze further. So we did the FFT for the quantum oscillation. If we look at this dash line, which is around 800 Tesla, so we can again see the peak around the 90 degree and 37 degree vanished again. So, and then we can make a clear plot here, the angular dependence of FFT amplitude. This repeats our discovery. At around 0 degree, we have the maximum amplitude, and then it decay quickly. At around the 19 degree, the amplitude nearly vanish, and then increase again, and then vanish again at around 37 degree, and then and so on. So this phenomena remind us a very famous effect, the spin zero effect in quantum oscillation. So next, I'm going to introduce the spin zero effect. This is the effect in Lifshitz cosmic LK formula. The change of resistivity is proportional to the RT term, temperature term, RD, Dingle term, and RS, the spin term, and finally the cosine term, the quantum oscillation term, and RT, RD, and RS are all phase mirror term. And here the spin zero effect is mainly coming from only coming from the spin term, RS here. So if we plug the spin splitting energy and the Landau level separation delta E in the RS, we will get another expression for the spin term, which is cosine half pi times the G factor times effective mass divided by the electron mass. And from this equation, we know usually the G factor is a constant, so we can assume G is a constant here. And then only the effective mass has the angular dependence. And as we said before, this orbit has a nearly two-dimensional shape, so we can assume this effective mass has a two-dimensional angular dependence. So the mass should be equal to the 0 degree effective mass divided by cosine theta. Then we can, so if we want spin term equal to 0, we need to set the G factor times effective mass divided by electron mass equal to 2n plus 1. Then the spin term RS will be 0. Then the quantum oscillation amplitude will vanish. So and so we have two angles where the quantum oscillation vanish. So we can plug these two angles in the RS term equation. Then and also plug in the electron mass at 0 degree. We have the mass plot on the right panel. At 0 degrees, the electron mass is around 0.79 electron mass. So plug this constant in, we can get the G value is around 15.6, which is a large number compared with 2, the electron G factor in vacuum. So next, we want to confirm our large G factor. Then we did the LK fitting for the our quantum oscillation. This here showed the two components LK fit model. You can see here the fitting is fit fairly well to our experiment data, which means the model is good enough for us to get some information like the Dingle temperature. From the fitting, we can get LK fitting. We can get the Dingle temperature is around 14.5 Kelvin. Then we can finally plug the effective mass constant, constant G factor and the Dingle temperature into the LK formula to make the fitting for the angular dependence of FFT amplitude data. So here the figure A showed our fitting. The red curve is LK fit function fitted the our data.
10 minutes.
Yeah, this is the last one. You can see here is roughly the fit function roughly fit our data, which confirmed our large G factor. But you may notice the second peak here, the red curve is a little bit larger than the measurement data. That's maybe because the scattering rate is larger at a higher angle. So which means the Dingell temperature should be higher at a higher angle. So if we set the Dingell temperature higher, we can get the figure B here, which fit better to our experiment data. So that's our experiment. In summary, the cesium compound is a superconducting topological Kagome metal under high magnetic field. This compound shows spin zero effect in SDH oscillation, and this spin zero effect, from this we can get the large G factor, which may indicate large spin orbit coupling in this compound. That's all I want to talk about. Thank you.
Thank you very much.
Thank you.